Good evening, dear participants and listeners. Welcome to our live channel that calls Fluid Mechanics. And I would like to introduce you. Our first speaker is Regina Iulmukhametova from Bashkir State University, and her topic is mathematical modeling of viscous incompressible fluid flow with suspended particles in rectangular channel. And I would like to remind you that our presentation will continue for 5 minutes, and in the end of sixth presentation, you will have chance to ask the questions of our speakers. Regina, you are welcome.
Thank you. Good evening, dear participants of the conference. Firstly, I would like to thank the organizing committee for the opportunity to take part in this event. My name is Regina. I'm a graduate student of the Department of Applied Physics, Bashkir State University, located in Ufa. My report is devoted to mathematical modeling of a flow of a viscous incompressible fluid with suspended particles in a rectangular channel. The flow of suspension in the channels are found in many areas of industry, for example, when applying hydraulic fracturing in oil and gas industry. We are studying the flow of viscous incompressible fluid with suspended solid spherical particles in a rectangular inclined channel. It is believed that the fluid is incompressible, particles have the same size, and flow is laminar. The mathematical modeling includes the equation of mass transfer and phase momentum written in the single fluid approximation enclosed by a boundary condition here. Here the approach of Gavrilov and Shebel is used. The empirical dependence on the viscosity on the concentration of particles is represented by the Krieger dependence, and it looks like this. The solution of problem is carried out numerically in open form. To validate the program code, we compared the calculation result with experimental data. The author studied fully developed profiles of particle velocity and concentration during suspended flow in a flat channel. Convergence is good enough. Previously, we modeled in two-dimensional flow of suspended in laminar model, studying the behavior of the suspension at different value of injection rate channel without walls. So using a simplified 3D modeling, we also simulated the flow in the channel. Good convergence was obtained with the experimental data obtained by our colleagues from the neighboring lab of our university. The result of experimental and numerical modeling of the dynamics of the distribution of glass spherical particles in a liquid stream and their deposition along the channel of the pressure drop of 20, 40, and 40 kilopascal are presented. Today, we study the dynamics of the distribution of particles in the flow and sedimentation along the length of the channel, depending on the values of the liquid flow rate and angle of inclination of the channel using a full mathematical model. The first result we obtained, in particular, you can see on slide 8, the distribution of particle concentration in the horizontal channel at different points of time. When the injection, we considered that the injection rate is comparable to the sedimentation rate, there is formation of a shaft in the inlet which grows over time and clogs completely. So when we with the increase in the channel angle, in particular angle of 45 to the horizon, 45 degrees, a shaft is formed in the near inlet, but due to the comparability of the sedimentation and injection rates, the particles don't propagate in depth until the area in the interest is filled, and filling of the channel is carried out more evenly. So on the next slide, you can see conclusions. And now the study continues. Depending on the angle of inclination, the injection rate, the sedimentation rate of particles, and
Regina, thank you so much. It was really nice, and in the end of all presentation, listeners will ask you questions. But now we have time to listen Christoph Marzec from Rzeszów University of Technology, and his topic is heat transfer distribution of surfaces under an array of impinging jets from various nozzle shapes. Christoph, you are welcome.
Thank you for introduction. I would like to present a topic which is addressed to the heat transfer distribution on surfaces under an array of impinging jets with various nozzle shapes. So, impingement cooling system plays significant role in many technical applications. It is caused mostly due to high rate of heat transfer and mass transfer between target plate and cooling fluid. There are a lot of examples of usage of cooling systems, such as photovoltaic cells cooling, such as gas turbine casing cooling, such as hollow blades of also gas turbine coolings. So I would like to present example of cooling systems based on active clearance control system. The abbreviation is ACC. So this is the cooling system which is installed on casing of low pressure turbine of jet engines. Here we can see a photo of such of cooling system, and it is composed of distribution tube, distribution channels, cooling holes which are located all around the distribution tubes and which are directed perpendicular to the target surface. The main role of impingement cooling system is to provide proper clearance between rotating structure, which is composed of disc and blades, and static structure, which is composed of casing and outer air seal. Those clearance is not constant during the phase of the flight of aircraft. At the beginning, we have nominal clearance, which is reduced significantly in the takeoff phase to achieve the minimum level. Soon after, when the blade starts to grow due to centrifugal forces and high temperature, the clearance starts to increase significantly to achieve constant level during the cruise phase. However, this clearance is not sufficient. Therefore, it's too big. Therefore, it has to be reduced using active clearance control system. However, current design of active clearance control system is not optimum. There are a lot of areas, especially confined areas, in which we have higher temperature than in unconfined areas. And this results in stress concentration in mentioned areas. So presented problem is addressed to provide high rate of heat mass transfer and uniform Nusselt number their delivery in cooled area. So the CAD geometry is composed of one distribution channel with 10 cooling holes with cylindrical convergent and divergent shape of the nozzles of the flow area and target plate. It was considered that fluid properties were constant, effect of gravity radiation was neglected, and the fluid was treated as incompressible. And of course, steady state assumption was assumed. Here we can see the cross section of presented problem. And in my analysis, various Y2D parameter was considered, various S2D parameter was also considered, and different nozzle shapes. Y is a distance between distribution channel and target plate, while S is the distance between neighboring nozzles.
Christoph, I'm so sorry, you have not so much time.
Okay, I try to be hurry. So method, of course, was verified using GCI index and comparison with Nusselt number full mass coming from the experiments. Of course, the match was generated using ANSYS CFX. 1.7 million elements was created, and in the boundary area of the flat surface, 18 layers of hexahedral grid was created, and in the area of the nozzles, 10 layers of hexahedral grid was created. And as I said, various Y2D distance parameter was analyzed, various S2D distance parameter was analyzed, and different shapes. Here we can see velocity vector plot for two exampled Y2D parameters. And here we can see the Nusselt number distribution across the whole 10 jets. In the stagnation region, we can see that we received high rate of Nusselt number, while for larger values of Y2D parameter, the values were much smaller. Here we can see results of the analysis, actually velocity vector plot for distance for various S to D parameters. We can see the fountain evacuation during to the neighboring heat of the streams. And this graph presents Nusselt number distribution for various S to D parameters. The values are much lower than in comparison. Yes.
Yeah.
Just 1 second.
Yeah.
Velocity vector plot for convergent nozzles and Nusselt number delivery, and velocity vector plot for divergent nozzles, and Nusselt number delivery. Here is one graph comparing all the results and the conclusions. So we can say generally that various Y to D parameter affects significantly Nusselt number and the heat transfer rate, as well as S to T parameter. And of course, the various jet geometry changes the heat transfer rate from convergent to cylindrical. We increase 28% of cooling efficiency, and from divergent to cylindrical, we increase efficiency 30.5%. Thank you very much.
Christoph, thank you so much for your great job. And we have next speaker, Varvara Manuilova from Corning Scientific Center, and her presentation is comprehensive pressure drop model for catalytic converters. Varvara, you are welcome.
Hello. As said, my work is dedicated to development of fast comprehensive model for the pressure drop of a catalytic converter. Catalytic converter is a part of exhaust system of vehicles and designed to clear exhaust gases. One of the widely used catalyst substrate types is cellular ceramic substrate, which represents an extruded monolithic honeycomb with many parallel channels running axially through the part. Since substrates are used for gaseous pollutant conversion, the channel walls are covered with catalytic coating, which reduces channel cross-section area. And usually coating is located in channel corners. Low substrate pressure drop is desired because high pressure drop leads to fuel wastage and decreasing of engine losses or losses of engine power. Nowadays, to estimate pressure drop, simple 0D models are used, and typically they are derived matching experimental data with total pressure drop estimated with the 0D model. The main goal of my study is to develop semi-empirical 0D model which will accurately predict pressure drop in the catalytic converters using 3D CFD modeling, and work covers only laminar regime. There are several existing scales in substrate, and my work covers results on channel scale. In this case, computational domain is small part of substrate cut in longitudinal direction. Substrate pressure drop was compared with experimental data, and total pressure drop includes losses due to sudden contraction, sudden expansion, and losses due to friction in substrate channels. To 0D model implies that for calculation of resistance coefficient F, analytical or empirical expression are used. So losses due to sudden contraction in case of substrate under laminar regime can be considered zero because there is no vortex upstream the substrate, and as soon as outlet velocity profiles are close to parabolic one, the formula on slide can be used, and it shows good comparison with results of 3D CFD modeling. For calculation of friction factor in square channel, analytical expression can be used, but as soon as velocity profile in the substrate outlet is uniform, not parabolic one, there is additional losses on the initial part of the channel, and this can be taken into account using correction factor. And to calculate friction factor of a channel with fillet, the linear approximation between cases for square and circular channel was used. On this slide, you can see validation of build model test matrix covered only almost 600 cases, and the improved model shows good results as for filters or for substrates without coating and for substrate with coating, as you can see on slide. Thank you.
Thank you so much. It was great. And the next speaker is Richard Petrov from St. Petersburg Polytechnic University, and his topic of presentation is optimization of the electric mechanical HVAC duct system based on gradient method. Richard, you're welcome.
Okay. So good evening, ladies and gentlemen. My name is Richard Petrov, and I'm a laboratory worker in Advanced Manufacturing Technology Center of the National Technology Initiative of Petrograd St. Petersburg Polytechnic University. Today, I want to talk with you about optimization in computational fluid dynamics. So me and my team has been working on optimization of HVAC system duct of an electric vehicle with our industrial partner KAMAZ. The main objective of this study is to develop a concept for optimizing the vehicle's air duct while achieving thermal efficiency when heating the windshield. Our research is based on aerodynamic optimization in the ANSYS fluid program. At the picture 1, you can see the position of considered ducts in the assembly of electric vehicle interior. Picture 1 and 2 describes the initial conditions of this task. The warm air flows into the duct from the bottom hole near the heater and flows out of the 4 outlets at the top of the air directly onto the windshield, thereby heating it. The finite warm model, which was used to calculate the flow, is shown in a figure 2. To solve the optimization problem, a converging solution to the aerodynamics problem is required. On this slide, you can see the averaged Navier-Stokes equation and the viscosity formulation. Due to the limited time, we will not dwell on this slide for a long time, really. This slide presents the formulation of the mathematical optimization problem. The function of the target, for example, can be the body's drag, lift, or a given pressure distribution, as in our case. The restriction functions are the Navier-Stokes equation for a 2-dimensional stationary incompressible flow. You need to find such project variables that satisfy the constant functions, and the goal of function reaches its local minimum. At this slide, you can see the algorithm of the optimization process in ANSYS Fluent, which we have formulated. Briefly, we start from the pre-processing, then the task is going to optimizer, and based on the flow calculation, the mesh is deforming until it makes the targets. And in the final round, we have STL model to post-processing. The figure 4 describes the MOV box, also known as mesh deformation area. We set this area so it doesn't change the initial conditions. As you can see from the image, inputs and outputs are not included in this area. The figure below shows the comparison of air duct geometry before and after optimization. So the gray one is initial geometry, and transparent green is optimized. After optimization, we made checking calculation, which results you can see in the image. As you can see, the scalar velocity field at the output has become more uniform. The blue zones with low speed became smaller. At the picture 8, you can see a finite wall mesh model with which we used to test airflow in the interior of a car before and after optimization. It consists of 45 million elements that makes it hard for computing at a usual personal computer. That's why we have resorted to high performance computing. We have resorted to the help of RS Polytechnic Supercomputer Center. The parameters of the supercomputer can be seen in the left part of the slide. The ANSYS syntax allows you to use number of cores as shown in the left image. So based on our contract with the Supercomputer Center, we used 512 cores to calculate the problem. And final, during the optimization, we managed to reduce the pressure drop by 24% and create a more homogeneous airflow at the duct outlets. To confirm the positive results of the calculation, we used optimized geometry and on its basis carried out CFD calculation, taking into account the interior of the electric car with the output of temperature fields on the windshield, as you can see at the picture 10. The prototype was made and its experimental research was conducted. The prototype is a modified card engineer of the initial design. The characteristics of prototype and developed optimized ducts are compared by CFD methods. Thank you.
Thank you so much. Our next speaker is also from Bashkir State University, Valiullina, and her topic is experimental study of the thermal motions of model emulsion in rectangular cavity with heating walls.
Good evening, my name is Valiullina and I want to present you my work about experimental study of the thermal motion of a model emulsion in rectangular cavity with heating walls. Emulsions are found in many areas of interest, especially in such industries as oil refining, chemical, pharmaceutical, and others. There are many works aimed at studying the influence of burial physical fields on the stratification of emulsion systems, but there are still questions that require further researches. One of these issues, the appearance and distribution thermoconvective flow in emulsions. We created an inverted emulsion consisting of water droplet dispersed in oil. In 100 millimeters of oil, 1 millimeter of 10% sodium tetraborate solution in distilled water was gradually added through a needle, immersed in the volume of the liquid, mixing with the top dry agitated and continued for 10 minutes. Emulsion samples were taken from the middle part of the cell. The photo of emulsion under a microscope is presented in the slide. It is shown that the emulsion is fully dispersed. The drops are distributed unevenly in the volume. The average size of emulsion drop was 40 micrometer. The viscosity of emulsion was 49 millipascal per second at 20 degrees above zero. To study the dynamic of dispersed systems, an experimental cell was developed. It is a rectangular vertical cavity with internal dimensions of 50 and 50 and 10 millimeters. Internal vertical walls of the cell are made of polycarbonate, horizontal of aluminium. It has used the cell structure with the possibility of heating places to simulate thermal convection. Creating a temperature gradient was carried out using two thermostats. In the process of establishing the convection flow, the shape of the flows changed. The most intense current were observed at steady state. At a finite time, four symmetrical flows were observed with two codirectional vortices in the lower part of the cell. There was also observed coagulation of droplets with subsequent coalescence due to the heat exposure. To study the propagation of the temperature front, the cell was upgraded. The shim of experimental cell is presented in the slide. Germanium lens was placed in the front of the cell to determine the temperature distribution using a thermal imager, while heating was performed on the left and right sides. Thermoconvective flow appears in the emulsion, the value of which can be estimated by the amount of distortion of isotherms in the picture of temperature distribution in the emulsion system obtained using a thermal imager when heated from the side. The temperature on the right side of the cell was 60, on the left 30 degrees above zero. So a stable emulsion was created with an average drop size of 40 micrometers. The origin and development of thermoconvective flows in emulsion system was studied. Thank you for your attention.
Milena, thank you so much. Dear participants, thank you so much for your great presentation. It was really, really interesting. Okay, the first question is for Regina from Bashkir University, and the man asks, what was the particle size and what was the material properties that was used to model particles?
The size of particles was about a half of millimeter, and as a material,
it was a glass particle.
Okay. In the experiment, yes.
Okay, thank you so much. The next question is for Christoph. Musin number characterizes the relationship between convection and conductivity.
Yes.
So which is the best result of work, and what is the most optimal Nusselt number you found?
Okay, it would be the best to share the screen to show the presentation if I can. So yeah. On my presentation, I just show the example results. but the answer is not so simple. So as I said, I just presented the example results. And if we go to the results, for example, for starting from Y2D parameter, so the distance between the nozzles and between the target plate, the closer distance we have, the higher values of the Nusselt number received. However, from the, let's say, application point of view, it's not good to have very close distance between target plate and cooling nozzles, because applications of very small distance, for example, in aviation, it's not possible, because due to, for example, vibration issues, we have to have at least a distance of 5 millimeters between the target plate and cooling orifices. So it means if we have nozzle with the diameter, let's say cylindrical nozzle with diameter 0.8 millimeter, the distance for Y2D parameter equals 1 will be only 0.8 millimeter. So it means that we will be very close to the target plate with our cooling system. So it is not possible to install such kind of system on engine. So actually, there is a graph, I do not have it on my presentation, it shows how the Nusselt number distribution in relation to the Y2D distance looks like for other analyses. But as I said, the smaller values we have, the higher values of Nusselt number, especially in the stagnation region, we receive.
Okay.
Also, I can say something about another analysis, for example, various geometry of the nozzles. Here the situation is rather simple, because from the analysis we received the data for the cylindrical nozzles, we received the highest values of heat transfer, so the highest values of the Nusselt number.
Okay. And what the result here?
Sorry?
And here, what Nusselt result was the best? 3.59?
Yeah, so here we can see on this graph for the cylindrical nozzles with the Y2D parameter equals 8 and S2D parameters equal 10, we received 4.6 average Nusselt number for cylindrical. It was the highest value.
Mm-hmm.
For
Okay.
from the graph we can see not the average but the general distribution of the Nusselt number, but we can see from this graph that for the cylindrical nozzles we received the highest values of the Nusselt number.
Okay, thank you so much.
Thank
The
you.
next question was for Varvara from Corning Scientific Center. What was the purpose of studying a square channel equation?
Because channels in substrate are square, so
Okay.
we use this formula.
Okay, it means in reality exists this
Yes,
type of channel.
in real part, the channels are square.
Okay, great, thank you. The next question was for Richard. Is it really important to make minor changes in duct geometry because the temperatures of windshield was less than 40?
Yes, I think because this work is dedicated to optimization of air duct of electric vehicle, and as you know, electric vehicle has at the moment of time really bad batteries, so every economy of electricity will be really helpful.
Okay, thank you so much. And the last question was for Vilena. How long does the stability last?
Thank you for question. We waited 30 minutes for convection to reach stable flow of convection, and then this stability сохраняется.
Okay. And did you estimate this period?
No, unfortunately, no.
Okay, maybe it's common for your future research to estimate how long you have stability system.
Yes, its problem will be studied in the future.
Okay, great. And what emulsion did you use in your research? What components was?
We created our model emulsion that consists of sodium tetraborate in distilled water, and this sodium tetraborate and water were dispersed in oil.
Okay, and why you decided to use these components? Why not another?
Because this emulsion was stable.
Okay.
We try a lot of experiments to make the stable emulsion, and it is the great one for us, for our experiment.
Okay, and what was the purpose of your research to estimate stability and that you did as goals of your research when you mix water and these components, the first you told us?
We want to make convection with this model emulsion.
Okay, but why these components? Because in reality, I have never heard such emulsion. Could you describe it where such emulsion can be used in real process?
Oh, it's just model emulsion, and we didn't want to get especially this emulsion. It's just stable, and we use this.
Wow. Okay, great. Thank you so much.
Thank you.
I would like to say thank you, all of you, for your great presentation, for your great research, for your really interesting results obtained in your research life, your period, and it was really nice for me, and I suppose for all listeners and participants. I hope so. And I would like to invite you on the next APM conference that will held in this year or and also in another year. I suppose you will receive more information a bit later. And I would like to thank you once again and have a nice evening. It was a pleasure for me to spend this time with you and to know more a lot of interesting things. Thank you so much.